Good afternoon. I welcome you to this session of experimental methods in fluid mechanics. Today we will be discussing about low pressure measurement techniques, and we will be discussing about McLeod gauge and Prany gauge and their operational principle by how we can measure low pressure, which is very low. And we have seen that rather we have discussed about U2 manometer, inclined well type manometer and different gauges, and we have seen that using those gauges we can measure pressure which is not very low but quite low to very high pressure. So if you would like to measure very low pressure, and then there are a few instruments, we should know them and we should know their operational principle. And to start with, today we will be discussing about the McLeod gauge, and we will see the principle upon which they operate and how we can measure a very low pressure using this device. So one important point that I would like to mention here, that measurement of low pressure, I mean experimentalist who will be using these kinds of devices, instruments to measure low pressure, they should take a special care. Rather I can say this measurement of low pressure needs, rather demands a considerable attention and a great deal of care, otherwise we cannot measure. So now we will see that the McLeod gauge, which is used to measure low pressure, we will see the typical range of pressure which we can measure using this gauge, using this device, and of course we will see how their operational principle. So we will now see the McLeod gauge. The McLeod gauge. So I will try to show the gauge schematically, then I will try to explain, and it will help us to understand the operational principle of the McLeod gauge if we try to describe through a schematic depiction. So I am drawing the schematic depiction of the McLeod gauge. These gauges, I mean this gauge is having different parts. So this is a schematic of the McLeod gauge. This is schematic, this is not at per scale. Now we can see from the schematic that the gauge is having 3 different parts, rather 4 different parts. One is this is known as valve B, this is known as valve B, and this point O, which is known as opening point, and right hand side extreme this is reservoir, and this portion, rather this tube is known as capillary tube, capillary tube C, and this is from vacuum space, from vacuums space, and pressure is say P, and this is reference capillary. So this is reference capillary. Now this is the schematic of the McLeod gauge. Now as I said that experimentalist who will be using this gauge to measure low pressure, he or she should take special care. We should discuss what are those care an experimentalist should take. So now rather I can say this is the modified mercury manometer. So this McLeod gauge is essentially a modified mercury manometer, and the reservoir, this dotted portion, that means this portion is filled up with the this dotted portion filled up is indicating. So this dotted portion indicates mercury filled up, indicates space which is filled up with mercury, which is filled up with mercury. So this is what we should know. Now how we can measure low pressure using this McLeod gauge. So now I will write the steps one should follow to measure low pressure using this gauge, then we will explain why we need to follow those steps, and while we are following these steps, then ultimately how we can measure pressure, low pressure using this gauge. So now I will be writing the the steps which we need to follow while measuring low pressure. So the steps for measuring pressure using the McLeod gauge. So one, I am writing, if I go to my previous slide, so the reservoir which is movable, I am writing here, this reservoir is movable, that means this reservoir location can be altered, so that reservoir can be lowered, or it can be taken at a higher level. So this is movable, reservoir is movable. So as a first step, the first step is the reservoir level the reservoir level or is lowered until the mercury in the capillary tube and valve drops, or mercury level, I can say mercury level in the capillary tube and valve, drops below the opening, drops below the opening C, the opening O. So, as a first step, what we need to do? We need to lower the reservoir. While we are reservoiring, while we are lowering the reservoir location, mercury in the capillary tube, also in the reference capillary, and from the valve, mercury level will drop, and the reservoir will be taken in a lower, will be taken further down until the mercury level drops below the opening point O. So, this is the first step. Now, while we are doing this, see, while we are lowering the reservoir location, and because of this movement of the lower reservoir further downwards, mercury level in the capillary tube, reference capillary and in the valve will drop, and at the same time a sample of low pressure gas is drawn into the gauge by lowering the movable reservoir. So, that means while we are lowering the reservoir, a sample of low pressure gas is drawn into the gauge, and also the mercury level in the capillary tube, reference capillary and the valve drops, and this lowering or the movement of the reservoir is continued until the mercury level drops the opening O. So, these are the first two steps. So, these are the first two steps we have seen, and while we are executing these two steps, we can see that the mercury level will drop, and at the same time the low pressure gas will be drawn into the gauge by the into the gauge, and these two steps the experimentalist should follow with a special care. Now, steps 3. So, the first two steps is important to know that we are bringing down, we are lowering, rather we are allowing the low pressure gas will be drawn into the gauge, and at the same time the mercury level will drop. Next, what we need to do? Next step is the reservoir is again raised, the reservoir is then raised until the mercury level crosses mercury level in the reference capillary, reservoir is then raised until the mercury level in the reference capillary is at 0. So, now if I go back to the previous slide, then the third step is then, since the reservoir is movable, now what we will do? We will take the reservoir slowly in its original position. Rather, we will have the movement of the reservoir off, and while we are having this movement, the mercury will now cross the point O, it will fill up the valve, it will fill up, mercury will now fill up the capillary, and also it will fill up the reference capillary, but the condition is that we need to have reservoir movement until, rather we will have a continuous movement of the reservoir towards the towards its original location, and this movement will be continued until the mercury level in the reference capillary, that is shown by the 0 point. So, the mercury level in the reference capillary is at the 0 location. So, maybe while the mercury is reaching at 0 location in the reference capillary, the mercury may not reach that level in the capillary tube, but the objective is to move the reservoir until the mercury level in the reference capillary reaches at the 0 location. So, this is the third step. Now, while we are executing these 3 steps, what is happening? So, now if we look at the second step, then what we can see that during the movement of the reservoir, downward movement of the reservoir, we have seen that the low pressure gas is drawn into the gauge. Now, the low pressure gas now is getting compressed whenever the reservoir is now taken to its original position. That means when the reservoir is moving off. So, what will happen, that the upward movement of the reservoir the consequence of this movement is that volume of the gas in the capillary, valve and tubing to the opening O is trapped and compressed into the top of the capillary. That is what top of the capillary. So, this is the consequence of the upward movement of the reservoir. So, now volume of the gas in the capillary, valve and also the tubing to the opening O is trapped and compressed into the top of the capillary. So, here we can see the top of the capillary, this portion is now having compressed gas. So, this is the compressed gas. So, because the gas which is getting trapped due to the downward movement of the reservoir will be compressed as the mercury level goes up. So now we will do small mathematical analysis. Say the cross sectional area of the capillary tube, not the reference capillary, is small a, and length of the region containing the compressed gas is y, we have Vc is equal to A into y, where Vc is the compressed gas volume. So here Vc is the compressed gas volume. So this is straightforward, very easy, that if the cross sectional area of the capillary tube is A and the length of the region containing the compressed gas is y, then the compressed gas volume is Ay. And if we consider that the volume of the branch, containing the valve above opening point O is Vb. So we are considering the volume of the branch containing the valve. So if we again go back to the slide where we have schematically depicted the McLeod gauge. So the gauge is having two parts, two different branches. One branch is having capillary tube and the valve, other branch is having reference capillary. So now the branch which is having above the opening point O, which is having valve, and the volume of that branch containing the valve above opening point O is Vb. So now we have understood that essentially what we are doing, we are taking gas into the gauge by lowering the reservoir location, and then whenever the gas is getting trapped in the branch which is having valve and the capillary tube. So now when we are allowing the reservoir to go up, rather we are taking reservoir to up in its original position, and the mercury level is going up, and the movement of the mercury will try to compress the gas which is getting trapped in the capillary tube. So and the process is continued until the mercury level in the reference capillary is at the zero location. So the gas which is getting trapped will have further compression. If we consider that compression process is isothermal, so if rather I can write for the isothermal compression. So for the isothermal compression of the gas, we can write, rather we have Vc into Pc is equal to P into Vb. So Vc is the volume of the compressed gas in the capillary, Pc is the pressure, and Pc is the pressure of the compressed gas. So Pc is the pressure of the compressed gas in the capillary. So this is for the isothermal compression process. Now the pressure difference this Pc will be definitely higher than P, because the gas is in the compressed state. We have compressed the gas by taking the reservoir in its original position, rather towards its original position. So it indicates that the pressure, the gas which is getting trapped in the capillary, and the trapped volume is pressure of the trapped volume is Pc. So Pc will be higher than the P, and the pressure difference Pc minus P, that is nothing but, so the pressure difference between the capillary and the vacuum space. So this indicates the pressure difference between the capillary and vacuum space, and this Pc minus P, I can consider this is Y in terms of the height of mercury column. So now if I go back to the this slide, where I have written the cross sectional area of the capillary tube is A, and length of the region containing the compressed gas is Y. So as if this Pc minus P, which is the pressure difference between the capillary and the vacuum space, and that we can write that is a length Y in terms of the height of the mercury column. So that is the height of the mercury column in the reference capillary. So that essentially indicates the pressure difference. So if we write a few steps further, then we can write this Pc minus P is equal to P into Vb by Vc minus P, that is P into Vb by Vc minus 1, because Pc into Vc is equal to Vb into P. From the previous expression we have seen for the isothermal compression of the gas, we have this relation, and just if we have plugged in the value of Pc I have written the Pc in terms of P, and we are getting this. So I can write this is Vb minus Vc by Vc. So this is again P into Vb minus Vc divided by Vc. If I go to the previous slide, where I have written the length, rather the volume of the compressed gas is A times Y, where Y is the length of the region containing the compressed gas, and this Y is again indicates that the pressure difference between the capillary and the vacuum space. So now Vc I can write in terms of A into Y, and that Pc minus P, so that means P into Vb minus Vc by Ay, this is the Pc minus P. So that is the pressure difference, and that is what we have seen. We can write that in terms of Y, that is the height of the mercury column. Now we can see that P is equal to, so P into Vb minus Ay by Ay, that is equal to Y, and P into Vb by Ay. So now if we go to the previous slide, where we can see that the Vb is much larger than Ay, because volume of the bulb is rather much larger than the volume of the compressed gas. So if we write this, that Vb is much larger than AY. So, then we can write that P is equal to AY square by Vb. So, P is equal to AY square by Vb. So, rather I can write that AY by Vb is much less. So, that is we have written that the pressure which is nothing but AY square by Vb. Note that, so the pressure, vacuum pressure, very small pressure, that is why we have used the terminology, vacuum space, very small pressure, which can be written in terms of A y square by Vb, where we know A, we know Vb, but what we need to measure, that is the y, length of the height of the mercury column. So, if we can measure y, and for that we need to have very accurate measurement, we need to take special care, and from there we can measure the pressure, because all the values are known. Now, one important thing is that we can measure very low pressure, of course, and the typical value we can measure using this McLeod pressure gauge is gauge pressure, of course. So, the gauge pressure from about, we can measure low pressure, very low pressure, even less than 1 torr or 133 Pascal, we can measure. But of course, the measurement of this low pressure we can have using this McLeod gauge, but using this McLeod gauge, if you would like to measure very low pressure, the experimentalist will encounter considerable difficulties, and he or she requires a great deal of care, otherwise he or she cannot measure. He or she will come up with the wrong measurements. Now, see, if you would like to measure very low pressure, which is even less than 1 torr or 133 Pascal, then of course it is quite straightforward that someone who will be using this gauge, special care should be taken. We have seen that there are many other conventional gauges like U-tube manometer, then other bellow gauges, diaphragm gauges. Those are there. We can measure with a low pressure, quite low to very high. We can measure even low pressure using those gauges with high resolution manometer or the diaphragm bellow gauges, but we cannot go beyond a particular value. So, if you need to measure which is extremely low, that we cannot measure using conventional pressure gauges. That is what I said just now, that diaphragm gauges, bellow gauges, and also the high resolution manometer, we need to rely on this kind of McLeod gauge, and other type is also there. But one thing is, the experimentalist should take a special care about it. Now, when we are talking about this McLeod gauge to measure very low pressure, we have seen that basically the movable reservoir, the movement of the reservoir towards the down, towards its further down, will allow the low pressure gas to be taken into the gauge, and in the next step, when we are taking the reservoir in its higher position, then the movement of the mercury will try to compress the gas which is getting trapped. Now, the movement of the reservoir which is continued until the mercury level in the reference capillary is at 0. So, the gas which is getting trapped in the capillary, which will have further compression. So, there is a possibility that the compression of the gas, so if the vapor is there in the gas which is getting trapped, and when we further compress the gas, the vapor might condense. So, that issue is only the important point we need to consider, and there is a possibility of having error if we do not take a special care on this aspect. So, again I am writing that if the gas, low pressure gas, so the main source of error I am writing, the main source of error in using a McLeod gauge arises from vapor in the sample gas. As the vapor, as the vapor can condense upon compression. And this, if we do not take care, and it may invalidate the relationship we have written in the last slide. So, if the sample gas is having even small amount of vapor, and if the vapor will start condensing as it compressed further. So, that is the main source of error a McLeod gauge have. So, but this issue should be taken into consideration, otherwise the measurement using the relationship we have discussed may not be valid. So, and as I said you that the measurement y, that is very important, that we need to measure, otherwise we will come up with the wrong results. And using this pressure gauge we can measure a very low pressure, that is what I said in the last slide, and only the one source of error, I mean we have identified that if the sample gas contains the vapor, otherwise there is no other major sources of error which our experimentalist can will face or will experience while measuring pressure using this low pressure gauge. So, now again I am writing this McLeod gauge are used, rather gauges are used to measure pressure from 0.0013 to 13.3 Pascal. So, we can see the range of pressure this gauge can measure. I mean the range is from 10 power minus 3 to 10 square. So, basically I mean of the order of 10. So, the huge range this McLeod gauge can measure, and so it is so measurement is so accurate and so difficult. I mean measurement is so difficult that we need to take special care, otherwise we will come up with the wrong results. So, the McLeod gauge is one of the gauges used to measure low pressure. We have seen and we have discussed about the operational principle upon which this instrument works. Now, other important gauge is there which is known as the the Pirani gauge. The Pirani gauge and the ionization gauge. So, apart from the McLeod gauge, there are other two different gauges available which are also used to measure a low pressure. One is the Pirani gauge, other is the ionization gauge, and the Pirani gauge, which is which exploits the reduction in effective thermal conductivity of gas with pressure in the regime of low pressure. So that means again we are using the one property of the gas, that is the reduction in the effective thermal conductivity of the gas in the regime of low pressure, and this is used to measure, in order to measure the pressure which is near vacuum pressure. So we can see that by measuring the change in effective thermal conductivity of the gas, of course in the low pressure regime we can say that we can measure, we can calculate the what is the a very low pressure which is close to the vacuum pressure, and we will discuss the working principle of the Pirani gauge, and also we will briefly discuss about the ionization gauge, and of course there are their schematic through their schematic depiction how they are working and the typical range of pressure they can measure, and of course several issues we need to consider while measuring pressure using these two gauges, and those aspects we will discuss in the next class. So with this I stop my discussion today, and we will continue my discussion in the next class. Thank you.